Welcome back. Now, there are other types of fillers for polymers as those of wood based fillers, synthetic fillers or carbon based fillers. Say silica based fillers are also available. Sand of fine particle size can also be used in the polymer as filler. Quartz, even if it is very hard, but it can also be used as filler for some product. Diatomaceous earth, pyrogenic silica, silica aerogel, then silicates, hydrated silicates are also used. Then asbestos, kaolinite, which is called china clay, mica in flake form, in particle form, talcum powder, calcium and aluminum silicate, these are used as fillers. Then glass based fillers, say glass in the form of flakes, glass spheres, glass that may be again hollow glass spheres, milled fibers means chopped or very short glass fibers, fibrous glass in the form of filament, rovings, woven rovings, yarn, mat and fabric. That means, glass can also be drawn into form of fiber, glass fiber, and from that glass fiber fabric is also made. Those glass fiber fabrics are used for thermal insulation purpose, for making some composites, glass fiber reinforced composites, glass fiber reinforced polymer composites, these are existing. So, this gives you a picture of different types of fillers used, and there are other than this glass and asbestos, silica based etc. Then metals, say metallic metal powders or metallic fibers are also used as fillers, metallic oxides are also used as fillers, say boron filaments, metallic oxides, say zinc oxide, alumina, magnesium oxide, titania, these are also used as fillers, whiskers, aluminum oxide, sapphire, beryllium oxide, magnesium oxide, thorium oxide, zirconium oxide, these are also used as fillers, calcium carbonates, say chalk, limestone, precipitated calcium carbonate. So, these are also used as fillers. Other fillers, say whiskers, again single crystalline fibers of very thin diameter, the aluminum nitride, beryllium carbide, boron carbide, silicon carbide, silicon nitride, tungsten carbide, barium ferrite, barium sulphate. So, these fillers or these fibers are used for making high performance composites, very strong and high temperature resistant, heat resistant composites. For making heat resistant composites to be used at elevated temperature, these fillers are used. Suppose there is a requirement from some motor vehicle company that we have to develop some heat resistant coating, surface coating for motor vehicles, for engine parts, motor vehicle engine parts, or some composites which should withstand 400 to 500 degree Celsius for some short period of time. It should not degrade, it should not be damaged. For that, then what is the polymer? It should be made with polymer, and polymers, majority of the polymers burn or degrade beyond 150 or 200 degree on prolonged exposure. But there are technologies available where even it is made of polymer, but those are very stable to high temperature exposure. Okay. Examples for particulate fillers: carbon black, precipitated silica, reinforcing category. I shall discuss later when I shall discuss the rubber products about the details of carbon black on those things and silica fillers. And again, to increase the interaction between a filler and the polymer, sometimes these fillers are little bit modified. say calcium carbonate, it is inorganic in nature. Can it be miscible with organic polymer? No. If it is not miscible, then it is inert. Then if it is inert, again to incorporate and disperse in a polymer matrix is a difficult task. It is not so easy, it is a very difficult task, because you have to disperse these fillers in fine particle form. Then you have to go for milling in a mixer machine or a blender machine at elevated temperature. So, it needs huge power consumption for mechanical milling as well as thermal input, heat input. Now, that can be improved if you can coat, give a thin, very thin coating to filler particle. Say, here is an example of this stearic acid treated calcium carbonate. Say, calcium carbonate is an inert filler, but you can easily disperse in a hydrocarbon or a organic polymer more easily if you can make a thin coating of organic material. Stearic acid, you know, stearic acid, fatty acid. Can you tell me source of fatty acid? Source of fatty acid? Vegetable oil. Vegetable oils are glyceride esters of fatty acids, triglycerides of fatty acids. So, those fatty acid can be taken from or extracted from oil, and that fatty acid can be dissolved in a solvent, dilute solution, then make a spray coating on these filler particles. What will happen? Solvent will evaporate out and there will be thin coating of stearic acid or this fatty acid on filler particle. So, it will be organically modified filler, and that can easily be blended with polymer. Now, here you are referred to one aspect of miscibility and solubility parameter. Miscibility, two components can be miscible provided they are of identical nature, is not it? Two friends can remain in one room if they are of identical mind, identical habits. If the habits are different, then they cannot stay for a longer period. Okay. You have to change their room. Here also, here also, if the two things are identical, then only they can have a friendship at the interface, friendship. One cannot remain without the other. Okay. That is the interface. Now, for that interface bonding, sometimes middleman is invited, some coupler is invited, marriage maker is invited. This marriage maker is nothing but coupling agent. Coupling agent. This coupling agent has got two hands of two different properties. One hand with one person, another hand with other person. In matrimonial affairs, what happens? Some middleman is there. He tells all the evils of brides on one side and all the evils of grooms on the other side. So, this way what happens? All the evils or all the good things, keeping your hidden the bad things. So, he makes the marriage this way, coupling agent, middleman. So, here also in case of this filler, if the filler is not compatible, if the filler is not miscible with the polymer, take a coupling agent. Say for example, silica filler is a very good reinforcing filler for polymer, but it is inorganic in nature. So, it is not miscible with these organic polymers. What is done? Normally some silane derivatives are used, silane coupling agent is used, say vinyl triethoxysilane vinyl triethoxysilane, please note down vinyl triethoxysilane, vinyl triethoxysilane. So, this vinyl triethoxysilane, it contains vinyl side means organic side and ethoxysilane SiO on the other side. So, it will make a coupling between silica filler and the polymer. So, here also stearic acid being organic in nature, it has got one carboxyl group polar side that will be oriented towards the calcium carbonate side, and the organic side, organic chain will remain on the other side, that will mix with the polymer. So, this is the basic principle. Okay. Rubbery fillers are used to improve toughness and impact resistance, because you know rubbers are flexible, soft. So, they will increase the toughness, increase the flexibility, etc., and impact resistance will be more. Fibrous fillers, again examples are there told. Plasticizers, this is most important thing. I told you what are plasticizers. These are low molecular weight organic esters, and provided the solubility parameter of the plasticizers are very close to those of polymers, then only a particular compound, particular ester compound can be useful as a plasticizer for one particular polymer. So, there are various large number of examples, say dioctyl phthalate, dibutyl phthalate, tricrysyl phosphate, dihexyl phthalate, triphenyl phosphate, dioctyl sebacate, etc., glycerol, resins. Now, you have seen some when this your on a frying pan, some dosa or something like that is made, some lubricant or some plasticizer, some oil is sprayed on the surface, then this is put and sprayed, and again it can easily come out of the surface, otherwise it will even stick to this thing. The principle of this plasticizer is almost similar, same type. Here the dioctyl phthalate, dibutyl phthalate, or some even some oils, etc., or say paraffinic oil, here you see glycerol or some resins. These increase the softness of the polymer, increase the flexibility of the polymer, decrease the hardness of the polymer. I gave you the example of that plasticized PVC. Okay. But being small molecular weight or small molecular size, molecular weight is low, what happens, whereas the polymer is of high molecular weight, it may be miscible, and while the product is made, what happens, slowly these plasticizers will diffuse to the outer surface, because it is soluble in the polymer matrix, it is mobile in the polymer matrix. So, continuous diffusion will be there, and the polymer will be under dynamic stressing, dynamic loading. Sometimes the surface is being wiped out. What happens? It is coming to the surface and surface is wiped out. That means that plasticizer molecule which comes to the surface, blooms to the surface, migrate to the surface, that is lost this way. So, slowly and slowly what happens? There will be loss of plasticizers from the product, and the product will become hard and brittle. You have experienced this thing on your cycle seat cover, that is plasticized PVC. When you buy it, it is very soft when it is new. In winter season, it becomes stiff, in summer it becomes soft, and after 6 months or 1 year of use it develops cracks, it becomes brittle, softness goes, because of what? Because of these plasticizers which are present inside, it comes out. Similarly, it happens to the footwear also. Footwears become, footwear say PVC footwear, that becomes rigid and brittle and cracks and breaks after 6 months or 1 year use. That is due to loss of these plasticizers, because this dioctyl phthalate, if you write the formula of this phthalate phosphate compounds, you will see the size of these molecules are low, and when these are blended with polymer, so these can easily come out of this, come out or bloom to the surface or migrate to the surface, and these are lost. So, initial purpose is served, but in the long run it is not stable within the polymer matrix. Then stabilizer, I told you the necessity of using stabilizer as ingredient in the polymer. The agencies are oxygen in air, ozone in air, ultraviolet light of sun ray, ultraviolet radiation of sun ray, or some chemical agency or microbial attack, okay, or thermal environment. So, these are the agencies to which if the polymer product is exposed, then that undergo degradation, What kind of degradation? Means those energies attack these bonds, chemical bonds, carbon carbon, carbon hydrogen, carbon nitrogen, carbon oxygen, carbon halogen, those carbon phosphorus, those bonds are present over there. So, those bonds will be exposed to these energies, these agencies, and they can sever the bonds. If they break these bonds, so the molecular weight of the polymer will be reduced, and the ultimate properties of the product will gradually decrease. So, that means the stability of the products are at stake. So, what you have to do? You have to increase the stability, so that the product is durable, Nobody wants that every 6 months you have to replace your cycle tire. Do you want it? That every 6 months you will be replacing your cycle tire? No, it should be durable more than 1 or 2 years, or after certain mileage. Say 4-wheeler tires, what is the durability? Do you know? 3 years, not through the years time only, but its mileage also should be counted, 60, 40,000, 50,000, 60,000 kilometers. After that it will worn out, it will be abraded out, or it will develop crack. So, there will be chunking out of the trade portion, or there will be catastrophic failure, bursting of this tire. Now, in order to prevent those failure, if you have to use certain stabilizers. Okay. Now, while rolling a tire through a road surface, the temperature goes high due to friction, and inside there is air. So, huge oxygen is there, outside there is oxygen. So, inside outside there is oxygen, as if the temperature is high. So, there will be thermo-oxidative degradation under mechanical stressing, mechanical as well as dynamic, periodic or cyclic rolling of the tire. So, under cyclic stress, under this oxygen stress, under thermal stress. So, under all this stress, this product is performing. So, its life has to be increased. That means, you have to prevent this its thermo-oxidative degradation, you have to prevent its physical breakdown also, for those we need anti-degradants, means which will fight with the degrading agencies. What happens when these products are exposed to those degrading agencies? That breaks a bond containing 2 electrons. So, if it is homolytic breaking, so 2 free radicals will be created. You know, these free radicals are highly active, energetic. Once a few free radicals are created on the product surface or within the product bulk, what happens? If it gets access to other agencies, or its process will be accelerated and it will break more and more number of bonds, and ultimately it will start a chain of reaction, chain of breaking reaction, bond breaking reaction, a chain of bond breaking reaction, you know, and there will be first degradation, first breakdown of the polymer chains, that means degradation process. So, in order to prevent that, if there is some anti-degradant or stabilizer, so it will just capture, it will scavenge, it will hold it like some defense person. If there is some miscreant going to do some crime, if there is some defense person, so he will catch him like this to prevent to do any crime like that. So, it will not allow it to further degrade, it will stop its activity there. So, that is called stabilization. So, degradation and stabilization. Degradation agencies, degrading agencies as those I have mentioned, and stabilization, for stabilization you have to use some anti-degradants which will fight with these agencies and stop their activities. So, UV absorbers, ultraviolet absorbers, there may be some ingredient which should be blended with the polymer that will absorb the ultraviolet light. That means, it will make a shielding effect, suppose. It will not allow the polymer to absorb the UV. So, that ingredient will absorb the UV, it will convert it to energy of higher wavelength, that means less harmful. So, from harmful to harmless situation, that can be done by some UV absorbers if the product is exposed to UV light. Heat stabilizers to protect against heat induced decomposition. Now, preventive antioxidants prevent generation of radicals. So, what happens if I show you a general suppose this is a polymer, some agency, suppose it is heat, it produces free radical, polymer radical and hydrogen radical. Now, this polymer radical, if it gets access to oxygen, peroxy radical, hydrogen radical gets to oxygen, access to oxygen, it will form hydroperoxy radical. So, this POO radical will further react with this polymer, forming P, H and even HO and POOH, large number of products will be formed. So, that will accelerate degradation this way. In order to prevent this, if you take some anti-degradant A, only Pa, harmless, this is harmless. Or it can react with A, this hydrogen radical can react with A forming AH, this is also harmless. Here you see these hydroperoxy radicals harmful. So, this also can react with, that means, so these are radical scavenging steps. I will show you in detail this degradation and stabilization of polymers later, not today, just I am mentioning here. Chain breaking, oh here the spelling is wrong, BREA, chain breaking antioxidants, chain breaking not, it should be BREA, chain breaking antioxidants means it will break the chain reactions. Degradation reactions, chain like reaction, non-stop reaction, that is called chain reaction. Okay. That chain will be broken, that degradation chain will be broken by such kind of radical scavenging steps, radical scavenging steps. Okay. Radical scavenging, that is called chain breaking reactions, and interrupt the propagation of oxidative chain degradation. I will tell you one example. You see wood, hardwood, say used for making furnitures. Now, those furnitures are stable, does not degrade, highly stable, even it can remain deformed, undegraded after 100 years or even 200 years of life. Why? Because it contains lignin. Lignin contains some phenolic units. These phenolic units, phenol, you know what is phenol? Phenol. Now, it can form quinonic structure also. So, phenol to quinone. So, this your phenoxy radical through resonating structures. So, it can lead to phenoxy radical, that phenoxy radical can give you some stable radical. That stable radical will scavenge those your degrading free radicals. So, you see phenol formaldehyde products, phenol formaldehyde composites are stable, that does not degrade. Oxidative degradation of phenolic composites are almost nil, minimum. So, wood products, woods which contains lignin, that is stable, because lignin contains phenolic units. Here you see phenols such as styrinated phenols, amines. Say amines are also antidegradants. Amines, amine derivatives, derivatives of ammonia, NH3. You replace one hydrogen of ammonia by a phenyl ring, okay, by aliphatic radical or aromatic radical, you will get aliphatic or aromatic amines. Again you can have amine derivatives. So, phenyl beta naphthylamine, PBN, here it is written PBN, What is PBN? Phenyl beta naphthyl amine. So, beta naphthyl group, phenylamine, you make a derivative of beta naphthalene. Okay. So, this way phenyl beta naphthylamine or other say alkyl derivatives of amines, say aniline, those are all antioxidants, antidegradants, and say two mercaptobenzimidazole. Now, here you see two bonds are there, NH and SH. These bonds can break, forming radicals S radical and N radicals here. So, these are stable radicals, that is why this is known as good antioxidant as well as anti-ozonant. Ozone is much more reactive than oxygen. So, it can prevent, this kind of compound can prevent degradation by the action of oxygen as well as ozone. 2-mercaptobenzimidazole. This is a Bayer Germany product, commercially available, MBI, or it is known as MBI. And other stabilizers are preventive antioxidants and peroxide decomposer, dialyl thiopropionate, para substituted phenyl phosphite, metal deactivators in the form of chelating agents. So, phosphorus derivatives, phosphoric acid derivatives or thiol derivatives, amine derivatives, say thiol compounds, amine compounds, phosphorus based compounds, these are used as stabilizers for polymers in general. Acha. PVC, now in rigid PVC technology, there is no plasticizer. I told PVC is a hard and horny polymer. How to make a product, how to fabricate a product? It is to be melted, but before melting it decomposes. Before melting it decomposes. What is the decomposition product of PVC? Do you know? Can anybody tell? HCl. That means PVC degrades by dehydrochlorination. So, PVC heat hydrogen chloride vapor, hydrogen HCl vapor, hydrogen chloride vapor that is generated. This is dangerous thing. So, PVC degrades at say this temperature beyond 150, and for making rigid PVC product one has to heat beyond 150. So, it can be done if some heat stabilizers is added to the PVC and then heated at greater than 150 degrees Celsius, no HCl generation. So, here using some heat stabilizer PVC can be protected, PVC degradation can be prevented. So, these are basic lead salts, cadmium and barium salts, organotin compounds. These prevents dehydrochlorination of PVC. Actually, prior to your this development of plasticizer till 1975, means mid 70s, there was no flexible PVC technology, rigid PVC technology was there, and there these stabilizers were used, but all these stabilizers, lead, cadmium, barium, tin compounds, these organometallic compounds are highly toxic. So, these were banned. Although these are good stabilizer for these PVC polymers, they are banned. Alkyl tin mercaptides toxic, dialkyl tin salts, these are also toxic, but less toxicity, mixture of this magnesium and calcium stearates, these are also used. Organic phosphates, aryl alkyl phosphates, triphenyl phosphate or epoxidized unsaturated oils, soybean oil act as HCl scavenger. So, here you see once these your cadmium, barium, lead compounds are banned, then these phosphates, organic compounds or epoxidized unsaturated oil. Unsaturated epoxidation of unsaturated oil means unsaturated oils contains fatty acid chains having some double bond, and if there is a double bond that can be epoxidized. So, that epoxidized unsaturated oils, similarly natural rubber can be epoxidized, ENR is available commercially, epoxidized natural rubber, that means the double bond is epoxidized, epoxy compound. So, those act as HCl scavenger. So, once some HCl is produced, that will be consumed by it. So, this way it stabilizes the polymer. So, polyethylene, PVC, polystyrene, polyesters and polypropylene are degraded by UV, ultraviolet light, at 300 to 370 nanometer range, and the polymers which degrade, the PE degrades at around 300, PVC at 310, PS at 319, polyesters 325 and polypropylene 370 nanometer. So, you see polypropylene degrades at 370 nanometer. So, polypropylene products are not suitable for outdoor exposure. You have seen this polypropylene oven sacks, cement bags, fertilizer bags. Have you seen those bags? Plastic bags. Today fertilizer is packed in polypropylene raffia tapes, in polyethylene raffia tapes. Okay. Similarly, cement, earlier the jute was the only packing material. Jute bags were used for packaging of cement and fertilizer. Today almost this jute has been entirely replaced by this polypropylene and polyethylene, but the reuse value of those polypropylene woven sacks today are almost nil. That means, after one use, it is never used for the second time packing of cement or fertilizer. And you have seen some people make tarpaulins, tarpaulin sets using these raffia tapes bags, but its life is very short. If it is exposed to sunlight, it becomes brittle. Acha. Also, you have some experience of using polymer rope. You say nylon ropes, those are not nylon, those are either polyethylene or polypropylene, majority of them are polypropylene rope. Now, if you use that rope exposed to sunlight, that means outdoor for your drying of your clothing. So, after 6 months it becomes brittle, it goes, it rots, that means it degrades. Here you see why this degradation wavelength is 370 nanometer, which is there in sunlight. So, it degrades. So, polypropylene is not stable, and polyethylene is little better, because polyethylene degrades at around 300 nanometer, which is very small, very small fraction in sunlight, but this around 370 there is that is present in sunlight. The bond energy required to cleave tertiary carbon hydrogen bond in polypropylene is 90 kilocalories per mole, around 318 nanometer wavelength. Okay. Now, you see EV stabilizers include some energy transfer agent, that means say these compounds like phenyl salicylate. What happens? I told that there may be some UV scavenger. So, these additives, say phenyl salicylate, act as a UV scavenger. So, if it is present over there, then what will happen? It will absorb the UV light and it will convert it to energy of visible in the visible range, that occurs through this chelation. See this chelation. This energy converts this compound, this phenyl salicylate, to this structure, then this through this chelation this energy is converted from UV to visible range. Achha, one more thing, carbon black, you see almost all overhead tanks are black, isn't it? 1 or 2% of carbon black is blended with this plastic HDPE, because this carbon black absorbs this UV without any harmful causing a harmful effect on the polymer. So, UV is absorbed by the carbon black. Before it reaches that carbon and carbon hydrogen bond of polymer, it absorbs. So, it stabilizes the polyethylene. So, they are carbon black, the use of carbon black not as filler, but as UV stabilizer, this tank. Okay. Other examples, benzotriazole, substituted acrylonitriles, nickel dibutyl thiocarbonate, pigments, carbon black 1 to 5% also gives protection against UV direction. I did quite a substantial quantity of research, substantial level of research in my lab on this degradation and stabilization of polymers earlier. So, my experience is that if you can develop any agency which can break to form free radicals, and if that free radical is stabilized to which it is attached, then that can act as a very good stabilizer for your polymer. Even there are some plants, say Moringa oleifera, drumstick plant, it contains natural antioxidants. There are many other plants, it contains natural antioxidant. Medicines we consume, those are antioxidants, majority of the medicines are antioxidants, because say any bacterial attack, say mucus secretion through nose or through rectum due to dysentery etc., that is nothing but mucus is nothing but dead tissue extracts, wastes, dead tissue wastes. That happens due to attack of tissue by those microbes, and that is a free radical process, that is as a degradation process, that is a free radical process. So, what we do? We take some protection by taking some antibiotic, those are antioxidants, anti-degradants, and that process is a free radical process. So, degradation is a free radical process and stabilization is also free radical process. Achha, this drumstick you see, it exudes some gum, and during flowering in the spring season what happens, the entire atmosphere actually remains full of pollens of the drumstick flower, that is preventive. So, that is a natural preventive in the spring time, that contains antioxidant. So, if those things can be extracted from plant and put in polymer, it can stabilize polymer. We have seen, we have some paper also, published paper on this. So, degradation of polymer by anti-degradants, a majority of this degradation process occurs through this free radical process. If it is free radical process, then you can think of a chemical compound available in the market, or you can extract from nature, then you put in polymer, mix and make a product, and that will continue the stabilization. Coloring matters, shades of pigments and dyes. Pigments are inorganic oxides and salts, inorganic oxides and salts. So, they should have high covering power and stable under processing condition. Now, you see, for white color what we use? Titanium dioxide, zinc oxide, good whitener, good white shade. Over that you can put a tinge of some other color, that may be again some inorganic materials, say iron, cadmium, copper, barium, chromium, compounds or oxides of these elements are good pigments, and these pigments are used in fine particle powder with the polymer for coloring purpose. Today you see this color, this color, this color, all are made from these coloring materials, either dyes or pigments. Normally the organic coloring materials are known as dyes, dyes, and inorganic coloring materials are known as pigments and dyes. And these pigments and dyes are stable under processing conditions, but they are having low solubility, and because of this low solubility characteristics, they lead to blooming, means migrating to the surface. Normally used as master batch or color concentrate. Master batch means how to, you see, these inorganic particles, pigments, how to blend with polymer, it is difficult. Small quantities used, that small quantities should be uniformly dispersed in the polymer, otherwise the color uniformity will not be available on the surface of the product and it will not be good looking. For that, say 0.5 part pigment is being used in a batch say 0.5 kg with 100 kg of polymer. So, 0.5 kg of pigment should be properly mixed with the polymer. So, it needs extensive milling involving power consumption, difficult. Normally what is done, a master batch is used, means where polymer is less, pigment is more. So, this way you take a stock of pigment and polymer, that is a master stock, a batch known as master batch, where pigment polymer ratio is high. You take few percent of that, and since it is already dispersed in that polymer, it will be easily dispersed in the final batch. So, what happens during this product manufacture, say master batches of colored your granules of this colored master batch is added along with the base polymer, and that will be easily mixed and product will be colored. If you go to some industry, you will see that is master batch or color concentrate, master batch or color concentrate. Titanium dioxide, iron oxide, it may be again yellow iron oxide, red iron oxide, brown iron oxide, lead chromates, yellow red chromates, yellow cadmium, green zinc chromate, iron blue, Prussian blue, ultramarine blue, phthalocyanin blue, blue and greens, other violets, magenta, red color, etc. These are available and these are used for coloring of polymers. Not only that, say colors of paints and surface coatings, Asian paints, Berger paints, they are competing with each other for different color shadings, you see, for coloring of your interior wall, outside wall, or coloring of any other object. So, those all of those contain these coloring pigments or dyes. Now, these colors are not actually friendly to living system. For living system, for some herbal color, herbal dyes are used, herbal dyes are available. Herbal dyes are used for coloring medicines, coloring foods. This color in food should not be made from this cadmium, zinc, barium, iron, but people are using. People are using, we do not know. These are cheaper. Instead of using herbal color, herbal dyes, they are using these inorganic, which are toxic, and putting into food. But we are somehow we are still living. Still we are living. Anyway, then lubricants, silicon fluids, graphites, stearic acid, stearates, calcium, zinc, lead, cadmium, barium, and as I told, acetyl palmitate, chlorinated polymers and other polymers which are soft, low molecular weight, low molecular weight polymers, oils, these are used as lubricants. There is no big difference between plasticizers and lubricants, almost simple paraffin oil, paraffin wax, those are also used as lubricants or plasticizers. Cross linking agents, no, your peroxides are cross linking agents, or some functional polymers, difunctional polymers, say malimides or diamines. For epoxies, diamines are cross linking agents. For saturated polymers of polyethylene, peroxides are cross linking agents, say dicumyl peroxide are cross linking agent. High energy radiation, say gamma radiation and X radiations are also cross linking agent, because they break the bond, one bond forming free radical, that free radical will interact with another free radical of another chain. So, forming some carbon carbon linkage between these two free radicals, so it cross links. So, if you expose a polymer to high energy radiation, it will become cross linked and its solubility will be low, lost, decreased because of this thing. So, I hope you have understood what is cross linking. We will discuss in little detail while I shall discuss with Rawer products. Flame retardants, there is no time today. Actually, each of these ingredient need a whole day for, or at least 2-3 hours lecture for elaboration. Flame retardants, okay. When I shall discuss with the Rawer products, there I will discuss this thing, flame retardants and composites, resins. Okay, I will discuss this thing in that class there. So, let us remain here today. Thank you very much.